Good morning. Today's lecture is titled A Viable Approach to Cellular Manufacturing for High-Mix, Low-Volume Manufacturers. It is a case study, and the goal is to show that when you apply methods like value stream mapping in a high-mix, low-volume environment, the ability to identify product families and be able to co-locate all pieces of equipment and support services needed to produce each product family, that is the foundation for implementing Lean. And this case study was actually work that we did at Superior Completion Services. So there is evidence that the data analysis and the concept come together. So when you look at people who talked about lean enterprise, this is again a slide taken from Brian Maskell Associates. The overall view has always been over the years that when you implement lean or you try to achieve the lean enterprise, you should go in three steps. So the first step is you pilot the implementation of production cells. The second step is, you try to make lean manufacturing widespread. And then finally, you try to run lean across the entire enterprise. While these desires and ambitions are noteworthy, it is well known that very few companies have been able to really implement lean at an enterprise level. I mean, Toyota still remains the benchmark. But when you look at this first step, pilot lean production cells, you can see that fundamentally the value stream is essentially a product family. So you identify the value streams, you map the value streams, and then you introduce improvements to the value stream flow. Now, core to that is the ability to do this. So a cell or focused factory can be designed if and only if the product family that constitutes its value stream is clearly and correctly identified. Now, in high volume assembly environments or just an assembly, it is sometimes often possible to say that this group of products, because they are variants of a particular configuration, can easily be assembled in a particular cell. But as you go lower down to upstream processes, machining, forging, fabrication, welding, injection molding, electroplating, heat treatment, it becomes a lot more difficult to even implement this concept of product family and appropriately the whole value stream management approach. So if you look, for example, that once you've implemented cells, when you look at the second phase, they'll say manage the business by value stream. Implicitly, in an implementation level, what it simply means is that whatever line or work cell or focus factory that you have implemented, make sure that there is one person who oversees its overall management of operations. So assigning value stream managers is as good as saying that a particular manufacturing cell should have a team leader. Okay, so core to this whole idea of going from just manufacturing work cells to this entire lean enterprise concept is that ability to be able to break down all manufacturing and assembly into these work cells and assembly cells, failing which that will not happen. So, what is job shop lean? I think it's just a blending of best practices. I, over the years, have learned a lot of the good work that others have done. All that I have done essentially is to bring it together and be able to implement certain ideas that over the years people have said ought to be done, but never really got down to doing to any specific form. So the first thing that I took inspiration from was this idea of focus, the ability to produce a family of different products whose design and manufacturing attributes are similar enough for them to be produced in a multi-product manufacturing cell or flow line. And this has been known as group technology from the 1960s. And group technology did not originate in Japan. It originated in Russia, and then from there it was adopted in Germany, and then it was adopted in Britain. And actually, it was all the writings and research in Britain that then kind of migrated to America. I, in fact, learned about group technology in India. So that's the first concept, focus, that when you try to implement improvements, you just don't go willy-nilly and say, let me eliminate waste. Okay. And so words like value stream essentially are built around this concept of focus. And focus is built around the physical concept of a product family. So from focus, you go now to lean. What is lean? It's just a buzzword, and from an industrial engineering perspective, what lean reduces to is the ability to execute all the processing steps to produce any product without waste in either in any steps to produce the product as well as between product steps when you are transferring it between two processing steps. So that's the second concept, that no matter what you do, if what you do is a sequence of steps, then essentially you are trying to eliminate waste at each step and you're trying to eliminate the waste between the steps, which is typically transportation and waiting. Now, everybody is saying, oh, we're all lean, we're all lean. But guess what Job Shop Lean pursues or aspires to do and has pretty much implemented? You also have to be flexible. And what is flexibility? My understanding of flexibility is the ability to adapt to changes in the mix and the volume of the products being produced. So when you're lean, the typical, application has been in assembly where you're usually making the same products or variations of the same product. So uh, a car is not different from a van, okay? Whereas a dishwasher is different from a car, okay? So flexibility is just having the ability to not only vary a production system to make a variety of products, but also to be able to adjust to the volume, low volume, medium volume, and high volume. And that is what brings this other concept that that you come to this thing called agility. Agility, in my understanding, is essentially the ability to flex, to be flexible, but remain profitable, but be able to be lean, which is control costs, maintain quality, and do well on on-time delivery. And that bringing together, in my own experience, having seen that it was done in the 1960s in many companies, is essentially this idea of the part family and essentially transforming most manufacturing facilities into a combination of flexible lines, flexible cells, and then what I would call a hybrid cell area or a mini job shop. So that's why this arrow which says the coming together of these four concepts. So everybody says, "Oh, let's be flexible and lean." But personally, if I may be very honest with you and throw water on your desires, being lean, which is flexible and lean, is hard. And I will leave it to you to go through these slides and look at each of these realities of most companies which are high mix, low volume manufacturers, especially those who operate as job shops, right? All of them face these challenges. And I hate to throw water on your desires, but when people say we wish to be agile and we want to be flexible, they have to understand that all of these operating conditions are alien to a typical Toyota assembly facility. And yet, if we if we learn about how to attack these challenges, that essentially is going from being lean to being flexible. And agility essentially is the ability to be quick enough when you're having to change or mix and volume. So when I learned about lean, that was in 1999, and I've read the book Lean Thinking, and then the Forging Defense Manufacturing Consortium had given me funding to basically start developing this whole body of knowledge that today is called Job Shop Lean. Uh, this was all I had. This is what I recognize as if any high mix, low volume manufacturer could achieve all these capabilities, they would be pretty flexible and lean. So come forward 20 years later, that's today. I mean, again, just as Toyota has a house of Toyota, which people have called the house of lean, I said that, look, we are basically going from being lean on one bank of the river to being flexible on the other bank of the river. So there is this bridge. And when you follow the five principles of lean that were first put forth by Womack and Jones, the three core capabilities that are needed to go from lean to flexible is this one. First one is group technology using data science. This whole idea of how do I form families of parts when I have, say, 1,000, 5,000, 10,000 so-called different part numbers in my database. I do understand that many of them may just be different because the part number was changed, but how to distill from 10,000 unique part numbers to, say, 2,000, and then in that 2,000 part numbers, how do I know how many part families I have? Because after all, every work cell I designed, every focus factory I designed is going to be built around a product family. So this is one of the requirements of the bridge, this whole ability to form product families. This then is the column that holds up the bridge on one end, what I would call a flexible cellular layout. This whole idea of be focused, but be flexible. But the equipment has to be arranged in a certain way. The support services have to be arranged in a certain way. The offices cannot be kept, on a different building. The offices have to be in a mezzanine that overlooks the production facility. And then the other column of the bridge is finite capacity scheduling. So the bridge of job shop lean, the skeleton is built around group technology, flexible cells, and finite capacity scheduling, never relying on material requirements planning and infinite capacity loading. And then, of course, all these vertical columns are your cables. The bridge is held up by columns. So each of these cables are the individual things that need to be done. So having equipment that combines additive manufacturing capability to produce the blank and then CNC machining to produce the finished part. I mean, that's the future. So I think that the more that manufacturers can have this kind of equipment where they are not looking for raw material to be obtained from overseas and then trying to have a very multifunction machine be able to make the part, it doesn't help that the machine is so sophisticated that the raw material has to cross an ocean. So each of these columns that you see here, the cables, are the individual to-dos that have to be implemented. And so what was explained in English here, you could come back and refer between the two slides. And that should give you a sense of everything that needs to be done, that I personally believe that either I'm able to do, or I know colleagues who can do it, or technology providers who can do it. So this is not to say that management and workforce capability are unimportant. If you see this thing called 4H leadership, I will discuss that later. You see this, skilled employees? I think it's very important to be flexible and lean. And of course, my bias has always been, do you have at least one well-trained, competent industrial engineer to help you with implementing the so-called bridge of job shop lean? So in my personal experience and bias, of course, is that cells are like the building blocks. If you want to be flexible and lean, you have to basically start with product families and work cells. And continuous improvement happens when you find that it is infeasible to implement cells. So then you say, well, how do I go to plan B or plan C, where in principle, yes, I'm still working around the product family concept, but because I have not been able to put equipment into work cells, how do I now maintain reasonably something called virtual cells? So where did this concept of cells come about? I mean, this is an age-old concept where people said that, do you or do you not have a functional layout? In a functional layout, identical equipment is kept co-located in things called departments. So here you have the shaping department, These are all the milling machines together. There may be different types of milling machines, two of one type, three of the other, but they're all kept together. And these are drilling machines, these are grinding machines, and then you have final assembly. But when you look at the physical flow of a product, it begins as raw material, goes to one machine. Then from there, it transitions across the department to one machine. Then from there, it transitions to another department. From there, it transitions to another department. And then finally, it ends up in assembly. And then the product goes out the door. Horrible. And to be honest with you, this was mentioned in the 60s when group technology first hit the waves. And today, still, I found out a very few clients or would-be clients, when you walk into the facility and you ask them, sir, can you please take me to the facility from raw to finished, they have basically left their equipment organized into these functional departments. And when you look at the success of the Toyota production system, one of the cornerstones is they have aligned their equipment naturally with the way the products would flow through different pieces of equipment. Okay, so this is not to take away from the fact that at Toyota, their managers have worked up through the ranks. And so they know how to manage people who are now doing their work. Okay, this is not to take away from the fact that good people being hired and trained and nurtured and incentivized is also a big secret of the Toyota production system. But at the end of the day, it's how you do work, how you make product that is also important. So many US manufacturers haven't even got out of square one, and then they claim to be, or they wish to be flexible, but they also wish to be lean. So when you look at going from functional layout to cellular layout, you can see that in the functional layout, the shop layout is not aligned with actual product flow. In the cell layout, the shop layout is aligned with actual product flow, and the entire product mix has been broken down into these product families. Okay? This is one product family, this is another product family, this is another product family, this is another product family. Now, you might be saying, well, when you look at the work cells, you have the same equipment now being distributed in multiple physical locations. So isn't there a loss of flexibility when you implement cells? Absolutely. And that is why when you implement cells, you also have to do something called product mix segmentation. You have to look at all the parts you're making or wish to make and segment them on the volume and similarity of production into something called runners, repeaters, and strangers. Runners, repeaters, and strangers. If you Google this term, runners, repeaters, and strangers, that was basically, again, a very old concept, but that was, again, the basis for saying that, look, we need to have what are called mixed mode manufacturing facilities when those facilities wish to make a high variety of product in different volume. You'll have some part of the facilities designed for runners, some for the repeater products, and the rest of the product mix will be produced in a job shop-like area of the facility. So the transformation from a functional layout to a cellular layout is a cornerstone of job shop lean. Again, all I'm saying is that this is what has been known to have worked in the 1960s in Britain and other European countries. I think where they failed was the people aspect and the management aspect. Toyota has figured that out. Unfortunately, since they are high volume assembly, a lot of their practices cannot immediately be transferred to high mix, low volume. So what do cells do? They basically attack work in process. So when you look at a functional layout, it is guaranteed to generate significant amounts of the 7 forms of waste. And you know how easy it is to pick that up? Go look for when you are walking through the facility, either as a Gemba walk or walking the floor of a product, you look for forklift activity. Look for forklift activity, and then you look for pallets, 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 pallets. This was the situation when we first began to implement job shop lean at Superior Completion Services. And the goals were pretty straightforward. We want to minimize the use of forklifts within the shop to the extent possible, especially around CNC machines. And two, we wish to have a complete handle on how many jobs are in queue, where they're at, and we wish to minimize the number of active jobs. And if you know Little's Law, it's a very simple way. There are lots of assumptions for Little's Law, but Little's Law basically connects that when there's a lot of work in process in the manufacturing system, it will take a long time to get orders out of the system. Very simple. So the more you cut down work in process and the more you make it possible through cells to get orders out quickly, you're going to have both quick delivery and you're going to have less cost of production. So this is an actual implementation of a work cell, and these are all the operational benefits of a manufacturing cell. I will not read them out one by one. I will leave them to you, but you can see again that all the benefits that people associate with lean can effectively be achieved through actual physical implementation of work cells. And there are, of course, support services and other things you can do to increase the benefits you gain. But going to work cells is also an alternative to continuous improvement, not necessarily calling it lean. So these are the operational benefits of a cell. These are the management benefits, and I would like to spend some time on that. How does a manufacturing cell get you some very important benefits that people attribute to lean? The first thing is focus. The cell doesn't do anything under the sun. The cell has a certain boundary, a certain focus in what they produce. And that helps because there's a learning curve effect. They become expert at producing any order, but they have a sense of, well, I produced this order in the past, this new order I received is kind of similar, I can do it. And the more you make the equipment flexible, the more it will be possible for that same cell to flex and make a variety of products. So that's the second thing, that the cell is flexible. I mean, the way you design cells in high mix environments is to create product families. And a product family is not identical parts. As long as that group of machines can make parts with this range of design and manufacturing attributes, it can be produced in the cell. There's the second benefit you get from having work cells, flexibility. Then you have this culture. That team is authorized to make any improvements they seek, and they can do it with whoever in the cell, whenever they wish to, as long as they make the improvements, and they can show that these improvements which we made impacted the performance of our team when it came to filling orders. Fourth benefit is accountability. You can no longer go and blame an individual. Now, the way that the cell is set up and the way the accountability is set up, typically the team responds and says, we did this right or we got this wrong, we will fix the problems that led to us failing on quality or delivery. So the team is accountable for meeting the metrics of safety, quality, delivery, productivity, and cost. And finally, this issue of ownership and autonomy. I don't know that most US manufacturers are ready for this, but it's a case-by-case basis. But I think, again, when you implement work cells, when your part family is correctly designed, when you have tried to bring support services into the work cell, when your metrics are correctly chosen, accountability is correctly driven, you get this ownership and autonomy. And to the extent that if somebody falls sick, the cell makes up for their absence. If somebody has a family emergency, the team decides to make up for that person's temporary absence. As far as even training, they can tell HR, we looked at the candidates that you brought in. We think that person X is a better choice than person Y. Much of this is where I think US manufacturers still haven't got it right. And a company like Toyota really has got it right because they've been doing it for decades. But these 5 capabilities or attributes a cell can easily, if correctly implemented and supported, could easily achieve. So what did we do? This presentation basically discusses everything that worked and did not work when we tried to implement the first pilot cell in the machine shop of Superior Completion Services. So naturally, when you go in and you don't have the data, you absolutely approach their veterans. So you look at their machinists, you look at their estimators, you look at their CNC programmers, and you say, well, you had said that you have a so-called cell. What do you think would be all the parts? What should be the family of parts that you would produce in this cell? So Steve Ward was the leader of that group, which did the brainstorming. They came back and said, these are the parts typically that we would want to run through this cell. But you will notice that besides the turning, there's a lot of milling, okay? And there's some coating, right? But when you look at that effectively, there's a lot of turning and there's some milling, and these are small to mid-size, part diameter. So this sample of parts that they showed represents about 60 to 70% of the range of parts that the cell is capable of producing. This was experience. This was experience. And you can never, never ignore that. So again, I strongly recommend that when you go into implementing Job Shop Lean and you wish to implement work cells, finding the product families and determining which machines will go into each cell to produce each product family has to be done with the complete cooperation and expertise of the people who've been making these parts. So once you have the product family, then you say, well, what machines do we put inside the cell? So naturally, it was very straightforward. We walked to the floor, we went to the lathes, and they said, yeah, you know what, these lathes get bar stock. This is the bar stock. This bar stock is cut on the saw. So it's the lead off machine, right? Then these were basically the lathes. And this was the milling machine that they said, well, if we could try to put these machines together, that would essentially do the turning and the milling for those parts that we think should be produced in this work cell. So this was the initial layout of the facility, and the color codes indicate the grouping of the machine. These are what are called functional groups of machines. So the color code will tell you that these are all the identical machines. So these were, for example, the three saws. These are some Washington lathes. These were the Mazak Milton centers. Okay. Then these were some manual machines up in the corner. So these colors indicate identical machines. And you can see there's a tendency that identical machines have been kept together. So when we took the parts that management agreed would be produced in this pilot cell, and then we went and walked the floors of those parts through the machines, guess what? They, in the initial state, this is how they traveled. Okay. So outside vendor is in the case where you have the shipping docks there. So if the parts had to go out, they would go out on that side of the shop. But you can see that whenever you implement work cells, automatically you're doing what Taiichi Ohno did in the 50s. He basically said, I will align my equipment in the natural processing flow of the products through those equipment. So this was how the parts flowed, and that was what he basically said. That, look, why don't we essentially, given that the saws are here, why don't we essentially take all these machines and try and bring it here? So you can see that once the physical travel of the parts is reduced, all the other benefits of lean can be systematically implemented. But that is key. Can you at least bring the necessary group of machines into a co-located area? If not, then you do continuous improvement part B, which is, okay, so how do I operate these machines in a virtual cell configuration? But that goal to make a family of parts in a cell configuration is absolutely essential for Job Shop Lean. This was the CAD drawing that was prepared for the movers to come and start moving the machines. And this was how the cell looked in different stages. So the saw is on this side. So this is the first two lathes, the VT36s. Then we put the VT26 here because we said basically let's allow some flexibility as far as workload balance. And then when you go to the other end, so now you can see that there's the two VT36s are here. This was the VT26. This is the saw up here, and this was the new Haas machine that was implemented. So this was how the new cell looks like, or at least looked like when it was kind of completed. So we had discussed the case where the pilot cell was designed with machine shop experience. But we wanted to know, look, have we correctly identified all the machines that should go into the cell? When we talked to the shop supervisor, the plant manager, and the machinist, they said, oh no, we've got the parts that come off these VT36s and VT20. They go all over the shop. So what that told us was that there was no discipline. This machine shop was running like any old job shop. Hey, I have capacity. The machine is free. Run this job. Nobody would care about, look, how much time did it take to set up the machine and to run the job? It was basically keep the machines busy. So we had to step back and say, look, is there any data that we have that we can basically use to understand that the group of machines we are putting and the product family that will be produced in the cell is going to end up being an autonomous mini job shop. So we took the data from the machine monitoring system called Synco, and what we tried to do essentially was to produce the FAST input file. So as you know, FAST is a production flow analysis software, production flow analysis and simplification toolkit. If you take the letters, it gets PFAST. So this is very interesting. Their ERP data did not have the actual routings of the parts. And what was the actual routings? How did those parts start from saws and move to various machines in the shop? Guess what? Today we have machine monitoring systems. So Danielle worked with a computer science friend of hers in college, and they essentially were able to take the raw data from the machine monitoring system, and then by collecting data fields associated with each job number, they were able to create the actual routing of the part. So the machine monitoring system logged particular part number, which machines it went to, on which days. And because there was a date and timestamp, it was very clear in what sequence those machines were visited. So guess what? We were able to take machine monitoring data, produce the manufacturing routings of the parts, and that is what helped us to populate the FAST input file. So the data was obtained. The data was obtained from Synco, and the analysis was done with FAST. What was the analysis we did? So these were all the machines. These were all the machines in the shop. And what we are trying to determine is, besides those VT36s and VT26s and the small mill, how many different machines was this part family being run across in the current state? So this was what is called the from-to chart. This is one of the outputs that FAST produces. And the beauty of the from-to chart is that it can tell you that from any of the machines in the shop to any other machines in the shop, we can tell you how many individual piece parts moved from one machine to the next. So that basically captures the usage and the heaviness of usage. This was the reality. So here we had the work centers that we had initially said, okay, let's put the lathes in the work cell. So what you see now is these machines were sending work to all these other machines inside the shop. And then we had all this other traffic between those machines themselves. So we didn't care much about the other machines. The bigger thing was, do we really need to put more machines into this work cell? And if so, what should be other machines? So when we did a Pareto, again, this is data analysis that is the topic for another lecture. But the point again is that once you have machine monitoring system data available to you, you can do some pretty nifty material flow analysis and machine usage analysis as a lead into defining the composition of a work cell. So these are all the other work centers you can see. It's a classical Pareto analysis. So we basically went and asked the machinists. We had Todd, we had Al, Tom, essentially everybody from the director of manufacturing to the plant manager to the shop supervisor to the CNC programmer to the machinists working in the cell. We sat down and we asked all of them, why were all these other machines used? Why? And this column, the comments here will tell you that there were some serious, shoulder shrugs that we observed that we don't know. But essentially, what was happening was that the shop supervisor was essentially saying, look, I need to keep the machines busy. Okay? So, without making effort to ask how much are the lathes in the cell being used, the moment that work came in, it was like, okay, we'll run the order first through these machines and then use some other machines. But why? Was it that they were unnecessarily running orders through these machines? And then because those machines didn't have the capacity being in the cell, the rest of the jobs had to be run on other machines. So when you have the data about how parts actually get routed through the shop, it really helps you to understand what do we need to put inside each cell, or even to step back and say, hey, do we even need to implement cells? Is cells the right implementation, or should we have a configuration like cascading cells or virtual cells? So once we knew what machines and what parts were going to be produced, this is what was done to actually implement the pilot cell. So keep in mind, strategically, we're basically saying, what can we do to make the cell work like an autonomous business unit? Work comes in, work gets done, work gets shipped. Okay, so the first thing was the 4H leader. I think that was very important that the director of manufacturing, Todd Chretien, took leadership. So I think that's most important. So there has to be clear knowledge across the executive group, the front office, and the shop floor that the director of manufacturing means business and he understands what needs to be done to implement job shop lean, and he's going to be there every step of the way to guide you, to mentor you, to help you, and to clear obstacles. So I call this the 4H leadership, and the H stand for head, heart, hands, and hooves. Now again, no human being has hooves. They're not horses or asses, but it just sounds pretty cool, right? 4H, 3P, 5S, So you can read the slide, but these are all the qualities that Todd Chretien possesses and demonstrated. And I think because of his leadership, everybody felt comfortable that if the boss is buying into job shop lean, we should buy in and we should support. That was the first thing, right? That everybody on the floor saw myself, Todd, and Hal, the plant manager, join almost every day in that corner, looking at what the work cell should look like. And we even had a whiteboard and we put post-it notes out there and we encourage employees to walk up and post their ideas on that board. That does automatic, right? We had this old clunking machine, and what people said was, look, we cannot have a standalone business if we don't update the technologies. That was basically a very key strategic decision. Let's go bring in a new Haas machine. So we upgraded the technology to make the cell capable and be able to do high quality work. We brought all the accessories of machine usage, so jaws, ring gauges, boring bars, to every extent that we could. We basically had these accessories being stored in cupboards along the far wall. They were in cupboards over here, way outside the cell. We just had the machinist say, what do you need? And all of that essentially was brought in. They repurposed an empty bookshelf, and poof, you know. Now there was no longer a need for them to go around the shop looking for a cart, roll the cart to the cupboards, look for jaws and gauges, and then roll back those accessories, use them, and then put them back. It was all they put right at the point of use inside the cell. Then we had the stenciling machine and where they put the IDs, right? So we had them in the stenciling area next to the deburring department, and they went and repaired one machine, and they bought that, and now all the stenciling was being done inside the cell. Now, the employee who was running the stenciling machines and doing the deburring, what he would do essentially is that on a signal, he would walk over to the cell and then take their parts that they had completed and essentially put them on this machine and stencil them. Over time, he taught the machine operators inside the cell how to operate the stenciling machine, and then they took over the work for him. So many good things happened where, the employees themselves saw, what, it's logical to now start working this way. And they took the initiative, and that's the beauty of implementing work cells, that it doesn't take change and apply it across a large enterprise at one shot. It breaks up that change into pieces, and it trusts employees to step up once they accept, yeah, this makes sense. This is a new way to work. It makes sense. Then we had threat protectors again. This stand was over here along the wall, right? And that's what they said. They said, okay, why are the employees having to walk out of the cell, look for scissors, cut these thread protectors in long segments, bring them back to the cell, and then slip these, sleeves on both ends of the part which had the threads. Because, if a threaded part bangs against another part or someplace else, it damages the threads, and that's so many thousands of dollars wasted. So once again, why are you leaving the cell? Oh, I'm leaving the cell to get thread protectors. Okay, guys, what will it take to put these thread protector stands one to each cell? Nothing. Okay, bring it in. Then, of course, this thing about toolboxes, right? At one time, every employee had their own personal toolbox. And especially from an inspection perspective, that's a nightmare, because the inspection department would like that all micrometers, gauges, be standardized and calibrated for their rules and their guidelines. But when you've got people using personal tools, there really isn't that control. So quite some time was spent to understand what should go into each of these toolboxes, and what should the first drawer contain, what should the second drawer contain, and then there was a rollout. Every machine had its own toolbox, and the machinists were allowed to have their personal toolboxes, but we made sure that all essential gauging and tooling was issued by the company and maintained and calibrated by the inspection department. This was up and down, this concept of transfer batches. So once the saw cuts the bar stock and puts the bar stock on a pallet, on a stand like this, what we did not want was inside the work cell, we wanted the machinist to say, okay, turning is the first step. Once I turn the part, let me move it to the next step, either the second lathe, the VT36, or the Haas mill. So it's a little hard to do one piece flow in a classic, assembly line context. Think Subway, they basic, or Chipotle. You ask for your sandwich to be made, and that sandwich goes step by step. Or in a Toyota assembly line, every car goes through a certain sequence of steps, one piece flow. We feel that transfer batches are the intermediate between a batch of raw material and the one piece flow that you seek. Because I think with transfer batches, you can have imbalance between processing steps, and you can allow for batch sizes to differ. So can't say we were very successful. These were the cards that they had, and you can see that they just still load them up because the surface allowed so many parts to be held. So what would happen? they would lovingly and dutifully make all of these parts and completely load the cart and then push it to the next machine. And then we had the lower level also. So we did try to implement a right-sized cart, but I wouldn't say that we really succeeded in getting that mindset out of the employees. So you can consider this improvement as iffy, as a work in progress, or basically, hey, try something new. But the good thing was that we did go away from having these pallets being put on the floor, all these pallets being put on these big cars. We did, what happened was Hal, the plant manager, one day came in and he removed these lower level shelves. It was basically a hole. So now nobody could put more parts on the lower level. They were at least forced that as soon as they finished this top surface and packed it, they moved the car to the next machine. I think it's a work in progress, and I think uh, this concept of transfer batch or one piece flow is going to vary with the individual application, the individual machines and products and cycle times and operator skills, and whether you have one person running three machines or one person to each machine. This was a very successful implementation, that of a water spider. So you've probably read about water spiders in the Toyota production system. Essentially, the machine shop supervisor, Tam, who is an expert machinist in his own right, he essentially became a water spider. And you can read through all the things that we tried to have him do. Sometimes it was maybe too much work, and I think you know, there was ups and downs in his day. But all of these activities, all of these activities, he essentially rose to the challenge and performed them. So the water spider is a logistics role, a position that in job shop lean is a given. Almost in every client situation, uh, I've personally pushed for that, for one of the better employees to be repurposed into a shop logistics position. And in fact, if you look at the robots of today, autonomous mobile robots, automate guided vehicles, just a matter of time before, robots on wheels, mobile robots, start doing this function of the water spider partially. Uh, but this was, I think, a very successful improvement that we made where the supervisor now took charge of ensuring that orders were on time, and then as soon as they were completed, he would personally pull the pallet jack or the forklift and move them to the next machine. It was a very successful practice that we implemented. We also had people from different departments who were impacted by the machine shop. We had them essentially move roles. So, for example, here you can see that the shipping and receiving department and the assembly department, their managers were, often, just meet with each other at least daily. We thought of having one manager, but again, what do you do with the second person? We did not go there, but there was this more of this cross fertilization. Again, it's a common practice, morning huddles, but it is who you put in the huddles and what they talk about that is important. Then we even had two employees from the shipping and receiving department now report to have machine shop manager. That created more awareness where they started seeing the parts that were being produced. And so when it came time in the cage, where all the parts were being kitted before they were rolled to assembly, now those people who worked in the warehouse became a little more savvy about what other parts we're looking for. And so when they looked at the kit, they would know which part was missing and then go either asking in the machine shop, where are you on this part? Or they would be saying, hey, has this part been misplaced in our own racks? So this was very important, and there was a lot more talking between the machine shop, the outside processes like heat treatment or coating or grinding, and even the outside vendors who sometimes were called in to make parts that the shop could not produce. This is a work in progress. Production controller and shop scheduler. We've had new people move into these positions. There's Vanessa Orango and Daniel DeWitt, but you can, and they are still kind of figuring out, who does what, and what software do we use, because they have now transitioned to Microsoft Dynamics 365 as the new ERP system, and the tactic scheduling software did not exactly prove to be usable. Okay, uh, too much overhead to use it. So these were all the functions that Vanessa and Daniel performed together, and this will be discussed in another presentation. But what we did do was, at a very high level, we had simple theory of constraints. So the saw is the lead off machine, right? And you saw that there were three saws, and the capacity in the saws was shared between the pilot cell, and all the other cells and machines that were going to be implemented in the shop. So we had to create a simple visual management device where there was one area set aside for the raw material which would be consumed in cell one, and this was right across from cell one. And then on the other side, they would put bar stock for the other machines in the shop. So at least we tried to get a sense of, do we have enough for cell one? And once we have enough for cell one, okay, now cut material for the rest of the shop. So again, there was a little bit of babying of what was done in cell one, but you can see again that some of the improvements don't have to be rocket science. And this was a very simple way to split the work buffer. So you control how much work is put into the cell, and you control how much work is put in the shop. So if you don't release raw material, you're never going to have any work in process. If you release too much raw material, there's surely going to be a growth of work in process in the shop. The drum buffer rope approach, again, because we had not implemented the other cells at the time that we were implementing cell one, we tried to create this job board. And again, I would hesitate, once you have, 20 plus machines and a job shop like environment, trying to track where every job is with, paper tags. So just we did try theory of constraints. We did try this concept of a buffer in the milling department. So, milling is always the second process, right? You always turn the parts and then you mill them. And, the mistake I think we made was we tried to keep enough work in the shop to keep the milling machines busy. And, that's not exactly the goal of the company. You need to get parts done, right? You need to produce the orders that need to be produced. Your obligation is not to keep people busy in a secondary department. So, while I do see the importance of shop scheduling, I would hesitate to push drum buffer rope approach of theory of constraints as something that's realistic in today's high tech environment. There are easily other approaches, especially with technology available, to implement finite capacity scheduling, but maybe not the drum buffer rope approach. This is again something which will be deferred to a later presentation, but once we had the Simco data coming off the different machines, Daniel essentially spearheaded very effective capacity planning and scheduling, and this was discussed in a recent paper in Modern Machine Shop. I'm going to cajole her, request her that when she has time to prepare a presentation. The same thing with shop performance monitoring. Everybody says OEE, and she basically combined machine utilization with job throughput. So that's another very detailed conversation that hopefully she'll present down the road. This was something which we were able to do with Simco again. Machine monitoring is a must-have technology, but my caution to all of you is please don't just use the machine monitoring the way that the vendors tell you to. I think that they're shortchanging you, and there's much more that can be done, but I think you need a data analyst type person, somebody like a Daniel Dewitt. She's the manufacturing data analyst and scheduler at Superior. So what we were able to do with the machine monitoring software output was we were able to create a timeline for every order that the shop shipped. And in this timeline that gets printed out, Yellow shows that the work order was in setup. Green, it was in process. And black is all the non-value added time. Guess what? You want to implement lean? Hmm? Data analysis and machine monitoring? Need lean. So when you ask why is there so much non-value added time, these are all the reasons. So job shop lean kind of looks at lean and pushes it to the 21st century. And it's common sense that when you have all this technology available, people are talking about IoT, Internet of Things, and machine learning, and smart ERP and fire capacity scheduling. And you have to ask, look, where is the data? And if the data is available, what are we doing with the data? And machine monitoring software is, I think, a must-have. Just that you should be a little careful about how you implement it, and are you in a position, do you have the personnel to really mine that data for gold? And this was work that was very impressive that Todd's team did. So what was the feedback about the cell? Well, good things. So this was an email that Todd Crescian sent out to his team, everybody in the machine shop. And this was November 2018. And I think I'd begun working with them about July. So that was pretty good. That was pretty good. So Todd was happy. His boss, Ed Smith, was happy. So we were happy. Then Nicole, who was then working as a shop supervisor and production controller, she sent an email saying, look, I was having a conversation with the cell leader. He likes what is going on in the cell. He's like, hey, can we get more cells implemented? So both Nicole was happy, and Hui was happy. He was one of the very friendly machine operators. And then finally, people outside the cell, you know, kind of got interested. So this was the machinist who ran one of the bigger, long bed lathes opposite the Kingstons. In fact, this is one of the Kingstons. So he sketched out what he thought the side of the shop which would make the big parts would look like. So, uh, the word got around. I think the good thing was that people were seeing that, look, the way Cell One is operating is a different way that the machine shop is operating. We're hearing good things about it. Management seems to be on board, and you start getting, I would say, good vibes from the other employees who have the interest and the smarts to maybe in the future run their cell. So what are the challenges? Right? The goal is to create an autonomous work cell where, you know, every river has its rapids and every good idea has its downside. So let me share with you things which did not go too well. And when things don't go too well, you basically do what is continuous improvement, right? So continuous improvement is not necessarily improving. Oftentimes, continuous improvement is trying to look at the root causes of failure or obstacles and saying, what can we do to overcome these obstacles? So here are some of the things which we did not succeed at, which I feel can be overcome, but not without pretty radical and aggressive effort from management down to the people who are opposing those changes being made. So here are some of them. So deburring, right? Deburring is noisy. Deburring is dust. And the deburring equipment was put away in a room in one corner of the building. Uh, Robbie Al, the CNC programmer, came back and said, not a problem. We can just put a deburring tool and an extra step in the CNC program. And now most of the parts produced in the cell will not have to be sent in a batch to the deburring area. So good things happened, right? It took time, but we were able to take this outside operation and absorb it into the cell. These processes, dirty processes, nah, you can't. Maybe washing you can put inside the cell, But phosphating, oh, you can look at these are steam tanks and acid tanks. No way, you cannot put phosphating inside the work cell. So guess what they did? They outsourced it. That has its own challenges, but you cannot bring phosphating into a CNC machining cell. Washing was pretty much determined that, yeah, we can just use the coolant spray that was anyway in the work cell and just dry it with the air gun that the machine is used to clean the chips from the parts. Oil dip, again, no way, too dirty. And when they had to put parts away for storage while the kits were being ready, that oil dip tank just had to be left where it was. Inspection was, you know, a killer. Why? Because in this particular facility, the machine shop was its own entity, and the inspection department was its own entity, and inspection viewed themselves as we protect the company from the customer. And so it was like, uh, it was, I would say, an unnecessary rock, an unnecessary barrier, but the culture was so ingrained. There was a director of manufacturing and director of inspection. There was a machine shop manager and there was an inspection department manager. And there was no meeting of the minds between those departments. So, what would that translate to? The classic evil of batch production. So, what you see here is that, so they get a large batch for, say, 200 part numbers, right? So, that cell would fill up multiple carts with all the parts. Okay, so only when they finished all 200 parts, that entire batch would be moved, like almost like a train, to the inspection department. And guess what would happen at the inspection department? That one inspector would one by one unload all these carts and put these parts one by one. Why? Because it was easy for them to take the gauge, check the same dimension one by one, and go right down the entire line of parts, then circle back and go check each part with the same gauge and each critical dimension, that particular classic batch mode. So if there were 4 dimensions to be checked, he would first get the batch, check one dimension all over, then second dimension all over, third dimension all over, fourth dimension. You want to see why, the shop was not running lean? Right there. But between you and me, and being realistic, that uh, these are some of the massive killers of lean implementation because of just the way people chose to do work. Again, why did they have one inspector checking the entire batch? Responsibility. And you might say, well, can't you split the batch and have multiple inspectors? Well, unless you standardize work, unless your inspectors have been around long term and are all equally skilled, how do you know that one person's inspection process is consistent with the other person's inspection process? There's a lot more in the story, but you can see that bringing inspection into the cell initially was a massive challenge. But again, uh, people got the idea. People understood that batch production and batch inspection was not very good for working process reduction and reduction of order flow times. So we began working on this idea that we tried to bring inspection into the cell. And you can see again that this granite table was put opposite the work cell. And there was an inspector who would walk from the inspection department here, come to the cell on signal, check the parts, and then when they were done checking, they would go back to the main department and be reassigned to other jobs. Is that perfect? No. But the fact that, within a few months, 2 powerful people, 2 directors said, you know what, we need to see what we can do to improve shop performance. And this needs both the machine shop and the inspection department to work with each other. But, to be honest, I think this first article inspection is pretty unique in the challenges it possesses. I heard from, in fact, another client in California who said the same thing. So I have a batch of, say, 20. I have to get the first article inspection done. It needs to use the coordinate measuring machine. I don't have the coordinate measuring machine next to my CNC machine. So the machinist makes the first part. It's a high precision part. It's an aerospace part. Then they walk it over to inspection. When they get to it, during that period, this machine which was set up to run this part just waits and waits. It's locked up. And only when the first article inspection is passed, then that first part comes back and the machinist continues and finishes the complete batch. So I don't have the answers, but I mean, that's a pretty important obstacle as far as, making a cell independent, getting one piece flow, especially when you have coordinate measuring machines, long cycle machines, and, the inspection department is a shared resource, which is, beholden to no individual cell. So we did get far. Cannot say that it was perfect by the time I left. I would need to find out what they've done as far as making inspection also self-contained to the cell. Ergonomics was another issue. You can see these big platforms. Uh, and when you have big platforms, while the platforms are good, they leave the parts at an easier height, and people don't have to bend down to the floor to pick parts off the floor. These big containers and pallets would imply forklift travel. Forklift travel in confined areas, not exactly safe. Not exactly safe. And what do these pallets encourage? Batch production. So just between these two adjacent blades, they would take the first stop and part by part transfer it here. So you had batch production again, right? What we did was, again, we had these carts. So what would happen is that when the machine filled up the cart, it would get inspected here, and then those parts would be put back. So even across the aisle, the washings were opposite from the cell one. We did at least get to using these carts so that a transfer batch was produced and inspected, and then another transfer batch was produced and inspected. So not perfect, but as long as the mindset is fertilized in people's minds that, look, keep thinking about what has happened with this part you finished. Does it go to the next machine, or it goes to a pallet, and how long does it wait? So typically, we're looking at cycle times of, say, 30 to 30 minutes per part, right? If you're making 20 parts of the batch, 30 minutes times 20 is a whole chunk of time, almost a full shift. So you are not sending that apart from that batch to the next machine until the batch is complete one shift later, even though physically, if just the mindset were changed and the handling capabilities were introduced, you could have made one and moved one. So while I'm not saying that, we have to absolutely dogmatically pursue one piece flow, even in a job shop environment, which is perhaps the most complicated manufacturing system, you've got to at least have an eye open. What is it that we learned from the turret production system that could be adapted, or maybe replaced, but at least adapted into a job shop environment? This was another one. So we had people from the machine cell here walk to this tool vending machine near the plant manager's office to get inserts. So they run out of inserts and they walk till here. This machine may not be working, right? So then what do? They say, oh, well, let me see. There are other machinists who run my kind of machine around the shop. So now they'll go walking around the shop looking for friends who will say, hey, do you have this insert? I didn't see these inserts in the vending machine. Can I borrow some from you? How much time does that go or take that machine in the cell is idle? So behind this vending machine, this room here, that's your tool crib. There were even more inserts here. There were boring bars, there were micrometers, basically many common tools that they could not afford to buy more of, they were all stored here. Half of them were broken. We had situations where boring bars with inserts on them had been robbed. Some machinists came in, didn't find the insert, they walked up to the boring bar, they unscrewed the insert, and they walked away with the insert. And now you have a boring bar which cannot be used. So what was the thought process? We uh, couldn't get the idea implemented for political reasons that I absolutely will not mention in public. But the basic idea was, look, why can't these inserts be managed in the individual work cells? So the thought was that could we basically have a vending machine put inside the cell? Or at least could we have it this way that once we recognize from the usage reports from the vending machine, the operators in cell one, we look at their usage of inserts coming off this vending machine. Could we basically have Kanban containers put inside the cell, like a two-bin Kanban, and when Bass Tool or AJ Rod or any other insert supplier came to the shop, they just looked inside each Kanban bin and they replenished the number of inserts per the min-max values put for that bin. So the idea was correct, but politically, I ran into a firestorm and realized that it's best to uh, not go there. But again, that's how you do continuous improvement by implementing cells. You say, look, why is the machine busy? Why is the operator engaged in non-value added work? Why? And once you find the root causes, you come back and say, okay, what can be done that this lost machine time, this wasted operator time can be essentially eliminated. And that's basically what drives all the Kaizans you do or the more involved projects you do. So this is something which I would recommend just about every machine shop to take seriously, that these vending machines are collecting data, and that again, get a data scientist in or an industrial engineer in and let them loose, either an intern or a full-time, but the data being collected by the vending machines, by the machine monitoring system, by the quality management system, oh, that's gold. In this, the 21st century, you have to work with what is called the hidden Gemba. It's not the physical workplace, it's the data Gemba. And the more that manufacturers in the 21st century get to that level, the better we will be able to compete. So these are all the other things, like I said, continuous improvement, and consultants are expensive and they have to be let go. But these were some of the items of work that were left that Todd continued with his group. So workload analysis, do we have enough machines? Or are we still sending work from the cells, from cell one to other machines? How often are we doing it? Could we be more efficient at doing it? Theory of constraints. Are we using the machines enough? If not, could we improve? Then we wanted to prevent the machinists from editing programs at the machine. There's this negative practice called dogging, and again, let's not go there. But then machine maintenance. Machines fail. Maintenance was not too well set up, but then they changed personnel, and that department began working much better. We wanted to have the cell operators maintain a performance board. That didn't go very well with the plant manager whose position was, well, they're not even educated, and they don't even know how to add. All sorts of reasons. But the thing again was that how do we know? How does the cell know how they are doing? Don't we owe it to them to be able to reward them or be able to guide them, be able to know where they need the training? Uh, this was important. Same thing. Now we don't know if we have the time to do that. My personal experience was the operators were gung-ho. Because like, you train us and we'll put that training to work. But management has to understand that they'll have to get away from running their machines. You can't just train in a vacuum. The same people being trained are not going to be running the machines. Um, we wanted to cross-train the employees, and that was another buzzsaw where the person who was running the lathe said, oh, I don't want to run the Haas mill. And the Haas mill operator said, hey, I was hired to run the mill. I don't want to run any lathes. And a little bit of a bring the hammer down had to be done to clarify that situation. But you can talk to Todd about what he did to rectify that situation where individual operators said, no, I don't want to learn the other machine. This was again another challenge. You can't be lean as a machine shop if your outside vendors or those who do individual processes like heat treatment or threading aren't on board with you. So if they're running to their own schedule and you're trying to be lean, that cannot happen. So this was again out of our scope, how to get in vendors and to also become lean, but to implement this concept of job shop lean. As you can see, implementing job shop lean just to get one shop aligned took more than a year, and that was just the starting point. We wanted to make better use of the machine monitoring software. Uh, Again, I think now that Daniel has come on board, they have the woman power to basically do that. Putting resident tools on all the machines in the cell, once again, this takes data. This takes data and considerable tooling analysis and engineering. It doesn't get done daily, quickly. So, hey, you want to implement job shop lean? Then just like lean, be ready for a long journey. Uh, Replacing mandatory overtime, Todd wanted to explore with that. While I was there, I don't know that we could do that. Uh, Setting up the teams to do huddles again. Um, it takes doing. It takes a full-time lean champion. Um, and if that position is not there, if HR is not too aggressive and HR, is happy doing their, typical HR activities. Yeah. So this slide essentially tells you that implementing even one cell takes a lot of effort. But the good news is that once we did this, they really ran with the transformation of the rest of the shop to kind of convert that to a mixed mode manufacturing. And I'll explain to you what is mixed mode. But again, first pilot cell, this is the beauty that you learn to do all the things you have to do to essentially achieve an autonomous business unit. And in some cases, you're left with saying, whoa, uh, management has to step in, purchasing has to step in, uh, IT has to step in and do these things also. But that's what teamwork is. But the good thing is there's a purpose. And what's the purpose? If we implement this cell, we get all the management benefits of implementing a cell. So this was the final result, what we call a mixed mode facility. So you've probably seen the movie Monster, so from that you can see Monster Highway and Minions. Minions, of course, is another uh, funny movie franchise, right? So what's Minion Lane? Minion Lane is all the small parts. So this aisle, this material handling aisle, what we essentially did was we said, look, in general, oil tool parts are big and small. Okay. Then, in general, oil tool parts are turned and maybe milled. In some cases, they're only turned. In some cases, they're turned and milled. So we basically said the shop should be divided into Minion Lane for small parts and then Monster Highway for big parts. Next realization was that, these Mazaks here, these are mill turns. You put the part in, you put the bar stock in, poof, it comes out finished, both turned and milled. So they left the Mazaks where they were and they put a milling machine opposite in the situation where there was a need for special processing, right? So this was its own little work cell, but small parts. I'm sorry, I don't know what these work cells are. That you can check with Todd. But now here, the Monster Highway is where we say, you know what, we can't have cells. We are going to go to something called cascading cell. And what does cascading mean? That we keep the machines in a functional group, but we allow the transference of parts or the splitting of batch to be more convenient. And we let milling machines be available right across from them. So the Kingston machines were used for really big parts. So we left them where they were. But the monster highway looked as follows: that we took machines by size capability and we put them into L or back-to-back configuration, and right across from them we put the billing machines. That was all that we could do. So again, uh, turn or turn and mill. So we had small parts on one side of the shop and big parts on the other side of the shop, and the cranes and the forklifts operated on the big side, and the carts, pallet jacks, and maybe once in a while the forklift operated on the minion lane side. So that was the big picture. This was essentially got implemented, and that was the massive transformation. And you can see again that as you implement the layout, you will automatically be driven to make other changes, the so-called continuous improvement. So I will not spend too much slide time on this one. Again, this is a big discussion, a lecture by itself, but you've heard about people saying, oh, continuous improvement, theory of constraints, lean, Six Sigma. And some people have said integrated TOC Lean Six Sigma. And then there's operational excellence. Everybody says, oh, continuous improvement, right? Personally, I feel that you can say bye-bye to all these buzzwords and you can stick with something which actually produces tangible results. So you can start looking at creating work cells. And how does the continuous improvement start? It starts with a thing called cluster analysis. So you take all your product routings and you cluster them. This is called the product process matrix. And these are called clusters. And these are called shared machines and exception operations. So if you want to see a value stream map that contains all your parts, well, it doesn't look like a value stream map. It's a spreadsheet, but it sure helps you to visually capture how different value streams belong in product families and how work centers are common across multiple product families. So you should start with this analysis. I'm not expecting you to do it, but today, fast, the software itself, and then data science software abounds. So you just need to get with a computer science department or a stats department, and you can get going with continuous improvement using manufacturing cells of product families as the basis for continuous improvement. And then once you get these non-ideal elements of the so-called product process matrix, these are two strategy maps, and you look at eliminating intercell flows, and you look at how do I run the entire business, the manufacturing business, when I have monuments and expensive shared machines external to the cell. So these are all the things you can do. These are all the improvement projects you can do. These are all the improvements you can make. As I said again, this is almost a lecture by itself, but this is again continuous improvement. And you get your value stream, you get your setup production, you get your quality control, you get your morning huddles. You can make all the improvements you want, but you're not using words like Six Sigma or TOC or Lean. And again, my last slide is this. If any company wants to become a lean enterprise, these are all the things they would do. Again, a big topic of discussion. You don't have to agree with me, but over the last 20 plus years of understanding, wow, getting a lean enterprise is pretty challenging. How did Toyota do it? And here, just working with medium-sized manufacturer, $20 million plus. These are all the things that need to be done. So if you have any questions, just give me a call. I'd be happy to discuss with you. Thank you very much. You know my email address, students. Just feel free to contact me. I will do my best to answer any and every question.